We're going to go over periodic trends. I've split this into two separate presentations because trying to put it in one made it obnoxiously long. So here we go. So for this set of trends, we'll define electronegativity and ionization energy, and then we'll explain the observed trends in electronegativity and ionization energy using electron configurations and the concepts of effective nuclear charge. So what is electronegativity? Electronegativity quantifies the likelihood that an element will pull electrons toward itself in a bond. It was developed back in the day by Linus Pauling, and it goes up to 4 as the most likely to pull electrons. So the most electronegative element is given a value of 4, and everything else is below that. There are a couple of 1s, but most things fall in the 2 region. Anyway, I like to think of electronegativity as electron suckage. How much does it vacuum up the electrons in a bond? I don't know why, but that image works for me. So, do whatever works for you. So the general trend in electronegativity is that it increases upright. The jump is larger when you go up a row than it is when you go across a period. So you're talking about the difference between an entire atomic orbital shell when you go up or down a row versus across a period where you're just changing how much you fill it. The most electronegative element is therefore fluorine. We ignore the noble gases for electronegativity because they're relatively unreactive and therefore unlikely to share electrons. You can find actual values for electronegativity with a quick Google search, but none of them were available in Creative Commons, so this is what you get instead. This will not matter in general until you take organic chemistry, but you can remember the trend in electronegativity for organic molecules in the top right corner of the table with the mnemonic Fonkelbricks. And yes, that did sound funny, Fonkelbricks. Fluorine is more electronegative than oxygen, which is more electronegative than nitrogen, which is more electronegative than chlorine, which is more electronegative than bromine, which is more electronegative than iodine, which is more electronegative than carbon, which is more electronegative than sulfur. Fonkelbricks. I promise that will make more sense when you're doing reaction mechanisms for organic compounds. But it's a way to remember it. All right, so let's talk about ionization energy. Ionization energy is the energy needed to remove 1 mole of electrons from a gaseous element in its ground state. That is a very specific definition. We can continue to remove electrons if we want to. So we could call the energy to take off the first electron the first ionization energy, the second one the second ionization energy, etc. You get the idea. We'll discuss the trend in first ionization energy in a little bit. For right now, let's talk about the trend in successive ionization energies. As you remove more electrons, you're increasing the influence of the nucleus on each electron that remains. There is more positive to each negative. We call that effective nuclear charge. And if we have time, we'll learn how to calculate it. But either way, as you increase the effective nuclear charge, it costs you more energy to pull off the next electron. Okay, so let's talk trends in ionization energies as we go from the first ionization energy to the 7th. I have color-coded these values to help me make some points. So the lower values are blue, and then we go to green, and lighter green, and then yellow, and then orange, and then red, and then dark red, and then gray, dark gray, and then black as we go on up. If you see the starred values, you will notice that they are all drastically larger than the value directly to the left. Why is that? Because those are core ionization energies. Why is that so much larger? Core electrons are closer to the nucleus, so it costs a lot of energy to remove them due to their higher effective nuclear charge. So they feel more attracted to the nucleus than the ones in the valence shell. You can see that the jump in energy from removing a core electron is substantial. For sodium, it is almost 10 times as large. The difference in values for sulfur, on the other hand, is closer to 3 times as large, which is still large, but not as drastic. So this shift can be attributed to the size of the orbital. or the atomic radius if you prefer. Sodium is larger than sulfur, aka its atomic orbitals are larger. We'll talk more about that periodic trend in the second part. A larger orbital is higher in energy, so removing an electron from a higher energy orbital costs more energy than removing an electron from a lower energy orbital. If you track across each element, higher ionization energies from left to right, you can see that at each additional electron takes a higher ionization energy. This is true every single time. As you go left for right, the numbers get bigger. But why? The amount of attractive force on the nucleus per electron goes up as the number of electrons goes down. So again, we're talking about effective nuclear charge. As you decrease the number of electrons, the effective nuclear charge goes up. You can also see that as you go across a period, going top to bottom on this chart, in general, it takes more energy to ionize the material. Not always true. You can see that I have made a box of lighter blue in the blue section, lighter green in the green section, etc. And that value is lower than the surrounding values. It does not follow the trend. So why doesn't it follow the trend? This is due to the way that the orbitals fill. So our first instance here is aluminum in the first ionization energy, right there. So what the heck is going on there? Aluminum has a full 3s orbital, and then it has one spin-up electron in a p orbital. So when you remove that electron from the p orbital, you have a full s orbital, and that is a more stable configuration. So the relative amount of energy to create that ion is less. Okay. Phosphorus. This is where we get another hiccup in the trend. So when we go down to phosphorus, all of a sudden we go up to a higher ionization energy, and then it goes back down again. And if you look, the second ionization energy, it hits sulfur. The third ionization energy, it hits chlorine, etc. Phosphorus has a full s orbital and a half-filled p orbital where everything is spin up. So we have 3 spin-up electrons. When you remove an electron from a stable half-filled state to a partially filled state, you can see definitely that trend holds. The second, third, and fourth ionization energies have a larger gap between the preceding value and the half-filled orbital, but you still get a blip in the ionization energy. All right, and then we have one more case. Removing an electron from argon costs the most energy because it is a noble gas with a completely full valence shell, which makes removing an electron costly. So we can look at the orbital folding diagrams to help visualize what I'm talking about here. So we have that next. So in our full valence shell, which are noble gases, but it can also be ions that are isoelectronic with noble gases, it will take more energy to pull an electron off of a full orbital than it will a partially full orbital, because it won't be radically different quantity, but it'll still be more energy to do that. In the second case, we're going to look at pulling an electron from a full subshell. So again, you're going from an energetically favorable state, in this case a subshell, to a less energetically favorable configuration, in the half-filled case. So this will be less of an effect than it happening to a full valence shell, but it will still be a thing. And you can see the trend in ionization energy 2, ionization energy 3, etc. No joke, it always appears. And then we have the spin up case. So if we have a half-filled orbital and we pull one out, that will take more energy than if we are just taking one off of a pair. All right. This is what they correspond to from that first ionization energy. Hopefully, that is helping you to get the idea that when you see an ionization energy, you should think of what it means for orbital filling diagrams to understand what the trend is. But let's look at this all a different way. Overall, the trend is increasing up and right, but there are exceptions, and luckily those exceptions are regular and their underlying reason is understood. As a general comment, the highest ionization energies are full shells and subshells. It takes more energy to pull an electron from a full orbital because it has a lower overall energy than a partially filled orbital. Lower overall energy is always favored. So disturbing that costs energy. And as you can see, we know this from previous stuff, the D block is kind of a mess. Right? There's weird stuff going on with the D and F blocks, and that's because of the way that you have the 4s and D orbitals, or sorry, the 4s and 3D, the 5s and 4D, etc. There's inconsistencies in how they fill, or perceived inconsistencies. It still has lowest energy configuration overall. And I think the bar graph on the left actually illustrates this trend better than the connected dots on the right. You can really see the dramaticness of the difference and the fact that the drama of the difference decreases as you go down in your group. Okay, so let's summarize. To summarize, electronegativity quantifies the likelihood an element will pull electrons toward itself in a bond. Its increasing trend is upright. Ionization energy is the energy needed to remove 1 mole of electrons from a gaseous element in its ground electronic state. The increasing trend is also upright for ionization energy, but there are hitches in the trend for going from full shells or subshells to partially full shell or subshell. It takes more energy than those of the surrounding changes. There is another hitch when going from all spin up to less than all spin up, so that'll be slightly higher energy as well. There is a trend in exceptions that continues as you increase ionization energy. So as you go from +1 to +2 to +3 to +4, you will see the same changes for when you have full subshells going to partially full subshells, for when you have all spin up going to less than all spin up, that kind of thing. And finally, ionization energy will increase for every electron you take off.